Hello, everybody. I will present our work from the group of advanced imaging technologies in Microsoft Israel on a fast global shutter image sensor based on the vertical overflow drain mechanism. So let's start. Professor Charbon gave us a very good introduction into indirect time-of-flight imaging, or ITOF. But I would like to mention that there is another subset of indirect time-of-flight, which is pulsed time-of-flight, where we don't use continuously modulated waves or illumination, but we use short bursts or pulses of light that the sensor shoots towards the target. The target then reflects the pulse back into the sensor, and you can see that, of course, the first photon to hit the target, meaning the photon that hit the closest target, is the first to bounce back, and the first to arrive back to the sensor. Now, if I have a very fast shutter that can truncate the light that is returning more or less in the same order of time that it takes the light to travel from the target, then I am able to cut off all the light that arrived relatively late. And that way I can have, if we'll rotate our imager, we can have every pixel integrate amount of signal which is proportional to the depth that the pulse of light traveled. And that is the base of pulse time-of-flight imaging. I'm going to focus more into the device in my talk, so I won't go into all the details from the algorithm point of view. So, in order to really have a good pulse time-of-flight camera, we need to have a good shutter. The shutter affects all of the properties of the sensor, and I'll name a few. First of all, the shutter slope determines the depth resolution. And that's pretty understandable. If I have a shutter that closes very rapidly, then let's say in the order of nanoseconds or less, then I can distinguish between pulses of light that came back from targets, let's say centimeters or even millimeters apart. The shutter efficiency, or the ability of the shutter to reject parasitic light from the scene, determines parasitic light rejection, or how we usually call it ambient light rejection. It determines my capability to work in strong ambient light environments, like in direct sunlight or in front of other illuminators. The shutter uniformity, or how the shutter operates over the entire array of pixels, determines a lot my compute power, because if each pixel shutter form varies, or if the shutter form varies largely between adjacent or far away pixels, I need to compute the depth differently to each one of the pixels, and that complicates a lot my depth calculation. So a good shutter is uniform, very efficient in opening and closing, and very fast. And in many cases, the need for nanosecond scale global shutter affects the device design very much. You all know that image sensors have gone a lot of advancement in the recent years, but the need for global shutter often affects pixel size and pixel topology, and you saw in Professor Charbon's survey that time-of-flight pixels are still much, much larger, maybe even an order of magnitude larger than modern image sensor, standard image sensor pixels. You need more gates to do, or even more electronics per pixel to do calculations. The resolution is also limited by the need for global shutter. First of all, because of the pixel size, because of the need to toggle a large amount of transistors and a large array uniformly, and the need to add circuitry for the calculation. And lastly, the power consumption of the sensor is, of course, affected very much by the need to toggle open and close the shutter many, many times. It is usually a very large capacitance that I need to charge and discharge, and it causes a lot of problems with power consumption. So I'm here to offer a new mechanism, which is actually a very, very old mechanism for doing fast shutter gating in image sensors. And this mechanism is called the vertical overflow drain. It is the mechanism that was used for global shuttering in interline transfer CCDs for, I think, at least the last 30 years. And there are still CCDs that are being produced with that mechanism. It is based on the pinned photodiode design, it is based on a pinned photodiode design. The pinned photodiode is an end diffusion that sits inside a P-well. And you can see that the P-well forms a potential barrier between the potential well of the photodiode and the voltage of the substrate. In order to implement this mechanism, you need the substrate to be N-type, and the photodiode is, of course, N-type, and the P-well between them is P-type, so it forms two PN junctions and a potential barrier. When we modulate the substrate bias, the substrate voltage, we can deplete this potential barrier between the substrate and the photodiode, and then make all the electrons sweep very quickly, drift very quickly towards the substrate. It's a very well-known mechanism, but naively it can't be used for time of flight or for fast gating, because how a standard CCD or pin photodiode pixel works. First of all, you reset the photodiode by elevating the substrate voltage. This is a TCAD simulation. It shows the potential maps in the pixel. So first of all, you reset, you clean all the charge from the photodiode, you sweep all the electrons to the substrate. Next is the integration period. You raise the shutter voltage. The shutter has now, you lower the shutter voltage, the substrate voltage, and you lower the gate voltage. And now the photodiode is like a floating diffusion that accumulates electrons. And in the final stage, you keep the substrate voltage low and then raise the gate voltage, and then you sweep the electrons on the way to the readout mechanism. The problem with this way of operation is, first of all, you need to toggle both the substrate and the transfer gate, and the transfer gate usually can't be toggled very quickly because it runs in thin polysilicon lines with bad conductivity, and it takes on the order of microseconds to toggle it. And it's also, the propagation time is very large and the capacitance is very large. Another problem is that you can't repeat the process because you reset the photodiode every time, and the charge can't be accumulated over a lot of pulses of the system. So our solution was never to lower the transfer gate voltage during the imaging. The way we do it is just keep the transfer gate voltage high, and then the potential map of the photodiode looks like this. Every electron that arrives, or let's say every photon that arrives, creates an electron-hole pair, and the electron is immediately swept into the floating diffusion or VCCD area, the storage area. So it happens very quickly, and when we want to stop the integration or to activate the shutter, we simply raise the substrate voltage, and then immediately the electrons stop going to the storage area, and instead every electron that is generated in the photodiode will be directly swept to the substrate. Now, the PN junction of the substrate is, or the depletion region is rather large, so it has a rather small capacitance. So this is a good solution also from the power point of view. So these are the waveforms of how to operate the system. In standard image sensor exposure, you start the integration by reset, by raising the substrate voltage, and stop the integration by raising the transfer gate voltage. And if you want to do it in fast shutter mode, You just keep the transfer gate voltage high all the time while you're toggling up and down your substrate voltage in order to open and close the shutter. Of course, this needs to be synchronized with the illumination. So we have this old new mechanism, or a new way to drive that old mechanism in order to produce a new application. And we need to characterize it, see how did we impact the performance of the image sensor. I must say that it opens a world of possibilities because interline transfer CCDs have been produced and have been optimized for a long, long time. They have very good quality, very good, very mature technology. And of course, they have small pixel sizes, large pixel sizes, very high resolution, very small resolutions. So it becomes a very flexible way to do imaging. So this is characterization system. Basically, we use the pulse laser and we sweep. We do a convolution of the picosecond pulse laser with the shutter form. That's how we characterize the shutter. I'm starting to talk quickly because my time is ending. And this is a typical measured shutter response. You can see that the rise time from 10% to 90% is very quick, is in the order of 1.5 nanoseconds, and the fall time as well. And the shutter contrast is about, or better than 1 to 100, and this is unprecedented in the time of flight, or at least in the indirect time of flight imaging world. Usually the contrast or the parasitic light sensitivity is an order of magnitude worse than that, so it has a lot of advantages in ambient light scenarios. And a lot of people say, okay, CCDs are dinosaurs. They have very large voltage, operation voltages, and they take a lot of power. But as you can see, most of the action of opening the shutter occurs over around 2 volts. So if you don't really care about the contrast ratio, about the parasitic light sensitivity, you can really reduce the amount of power that you consume. And another question that is often raised is, do I affect the quantum efficiency? I need electrons to travel very fast, so maybe I don't gather all the electrons from the sensor. And the answer is that we characterized it, and the quantum efficiency is not affected at all if we compare it to the same image sensor in standard operation. So every photon that we would have collected if we operated the sensor normally is collected in this way. Okay, these are some results that show the uniformity of the propagation of the shutter. We measure different sensors, so we see sometimes concentric propagation, sometimes linear propagation, and in some cases where the shutter is driven uniformly before entering the silicon, we can get completely instantaneous response from the entire array of under 200 picosecond difference. Another problem is the pixel-to-pixel variation. This is usually a problem that arises from process variations. The electron velocity inside the photodiode is not very stable in some cases, and this is solved or by better pixel design. It's very easy to solve it by reducing the full well capacity and the pinning voltage of the photodiode, or by raising the transfer gate voltage, which is always the easy solution. Another issue is contrast ratio. The contrast ratio is affected by the angle, the principal angle of illumination that arrives to the sensor because of shading by the transfer gate. But again, it's an issue that can be optimized by pixel design. And finally, an issue with this method is the dark current buildup, because the transfer gate is in high voltage for the entire duration of integration. We actually deplete the buried channel that is usually formed under the transfer gate in CCDs to keep dark current low. The traps become activated, and then the dark current count really increases. But there are ways to overcome this as well. I don't have time to detail. So, summary. We use a very mature mechanism that can be utilized, or we discovered a very mature mechanism that can be utilized for time-of-flight imaging, transient imaging, and other applications. There are many potential image sensors on the market that can be used. Several new parameters, we had to develop new methods to characterize them. And it's important to obtain really deep understanding of the pixel design in order to implement this new method correctly. Thank you.